Okay. Yes, okay. My brain didn't remember off the top of my head. Okay. All right. How you guys feeling? Mostly nodding, mostly smiling, at least smirking. It's Friday, the weekend is nigh, so let's get through lecture and get on to weekend quickly. Before we continue our two-dimensional vectors in lecturing, someone has asked about some of the homework questions. And I encourage you guys to ask about homework in class because odds are someone else is having a similar issue. And if I can talk about it in class, then I can address it for everybody all at once. I've got a few homework questions that I want to briefly go over. First, this is chapter 1 and 2 homework, question number 9 about the tortoise and the hare. Whoever wrote this textbook decided to put some numbers to that old fable. And in this particular question, you are told that everyone's homework is going to be slightly randomized. So if you're looking at your own work and you see a red number, that's a number that was randomly generated for your assignment, and someone else won't have exactly the same number in that space. But everything else, the black text, is the same. So every student will have the same basic question, just a different answer because different numbers go into it. Now, I do encourage students to work together. It just means if you're working together, you have to figure out the right method, and then everyone plugs their numbers into it. So do help each other, you just can't copy the answer directly from your roommate. So in this situation, we've been told the speed that a tortoise can run at and told that a hare can run 20 times as fast. So I've written here, based on my sample numbers, velocity of a tortoise, 0.15, velocity of a hare is 20 times 0.15, so I've gone ahead and just listed 3. We are told that they're going to start this race at the same time, but the hare immediately falls asleep for some number of minutes, and that the tortoise wins the race by a certain distance. If I was to give an image to that, and if this is the entire racetrack, the tortoise runs the whole thing, and in the 3 seconds that the hare is running, it covers most of the track except the length of the tortoise itself. So by the end of the race, the tortoise's nose crosses the finish line, the hare's nose is equivalent to the tortoise's tail. And your goal in this question is to figure out both the length of time the race takes from start to finish. So you hit a stopwatch right as someone says go, and then you stop it when the tortoise wins. And then separately, what is the physical length of the racetrack? The distance the tortoise ran, basically. So again, just putting numbers to the old fable. And the issue that students read this question and then come across is, all you're told is the speed of the two creatures, but at that point you might get a little bit stuck because the velocity formula tells us velocity equals displacement over time, but you weren't told the displacement or the time running for either creature. And so this is kind of the puzzle of this particular question. On most assignments, there's going to be most homework assignments, there's going to be one question that's kind of designed to be tricky, to make you think. And that's because the homework is, again, kind of free practice. You work on it until you get it. And one question out of 10 that's the really tricky one, getting it or not is like a difference between an A+ and an A. Same thing on my tests. Everything's weighted to where if there's one tricky question, getting that question flawlessly versus attempting it is the difference between an A+ and an A. So what I mean by that is if you don't get the tricky question flawlessly, that's fine. The course is waiting for that. This particular assignment, since it's 2 chapters, does have 2 tricky questions though, so keep an eye out for that. For this tricky question, the scenario that I propose to solving it is what I call 2 equations, 2 unknowns. Here we have two equations and four unknowns. The equations being equation one, the velocity of each animal. You know the number for velocity, but you don't know how far either creature runs or how long it takes them to run the track. But we have enough information to describe the hare's accomplishments in terms of the tortoises. Again, we aren't told the total distance of the track, but we are told that both animals run the full distance, barring the hare. It runs the full track minus the length of a tortoise. And so what I'm going to do is, I'm going to rewrite the velocity equation for the hare. Instead of its speed being equal to its displacement over time, I'm going to write it in terms of the tortoise's displacement. Because the question tells us that however far the hare runs is equivalent to how far the tortoise runs minus the length of its shell. So instead of delta x hare, I'm rewriting it in terms of delta x tort. So what the question tells us is that delta x hare should be equivalent to delta x tort, but minus however long your tortoise's shell is. Separately, we also have enough information to rewrite the hare's running time in terms of the tortoise's running time. Tortoise is running the whole time, so however long the race takes, the tortoise is running for all of it. But the hare is asleep for some number of minutes. So the hare is only running for a minuscule portion of however long the whole race takes. So if we were to try to describe the hare's time in terms of the tortoise's time, instead of delta t hare, I'm going to write delta t tort minus the length of time the hare was asleep. I've got 1 minute. I'm going to turn that into 60 seconds because we prefer seconds over minutes in this class. And our velocities are in terms of meters per second. So however many minutes you've got there, convert it to seconds before you do what I'm doing here. So this process is, again, just taking all of the hare's unknowns and rewriting them in perspective of the tortoise's unknowns. So we're just comparing the feats of the two animals based on the differences that we know between how they ran. So now instead of two equations with two unknowns apiece, we now have two equations with the same two unknowns in them. This equation, 0.15 equals delta x tort over delta t tort, and this equation can now be read as 3 meters per second equals delta x tort minus 0.2 over delta t tort minus 60. They've both been made in terms of delta x tort and delta t tort. And so now they have the same two unknowns in them. And this is a trick that we're going to use often enough in this class that I call two equations, two unknowns. If you have one equation with two unknowns in it, like for example, if you try to use the Pythagorean theorem on a triangle that you only know one side of, you're not going to get anywhere. You can't solve this for either A or C. But if you have a second equation with the same two unknowns in it, you can combine them together and kind of skip past the fact you don't know one or the other. I'm just going to demonstrate this. I'm going to take this first tortoise equation and rearrange it slightly. So 0.15 equals delta x tort over delta t tort. And using algebra, I'm just going to send delta t tort over to the other side and get delta x tort equals 0.15 times delta t tort. Same equation, just rearranged. And what this tells us is in any of these equations where you see delta x tort, you could instead write 0.15 times delta t tort, because delta x tort is equal to this. Anytime you see this, you can replace it with this. And that includes in the revised Hare equation. So now, I'm going to take delta x tort equals this and pop it in here instead of delta x tort. So we had 3 equals delta x tort minus 0.2 over delta t tort minus 60. And I'm instead going to replace the delta x tort with this. 0.15 times delta t tort. That's a lot of steps, but upon successfully doing this, this equation now only has one unknown in it. The same unknown is in 2 different places, but it's the same unknown twice, delta t tort, delta t tort. And so now it goes from unsolvable to annoying but solvable. Does that summary track? Annoying but solvable. So the goal now becomes, 1, making sure that your correct altered numbers are placed in here, because you'll have a different Hare speed, a different shell length, a different tortoise speed, and a different time of sleep. But once your correct number's in there, you just have to take this and solve it for delta t tort equals number. And then that would be the answer to the first part. And then once you have that number successfully, and you can check that your A is correct before moving on to B. There's no penalty for leaving one blank. Check that your first one's complete. Once you know that you have a correct number there, you can then take that number you found for delta t tort, pop it into any of your previous equations to solve for delta x tort. Because the distance the tortoise runs is the full length of the track. How's that feel? It's an odd math trick. We're gonna do it multiple times. We're gonna make sure it makes sense. And as a further reminder, the homework's not due soon. So if you don't get it now, we're gonna keep reviewing it. Does that feel? How does that feel? Questions, concerns? At least one thumbs up. Okay. Again, I encourage you to ask homework questions in class so that I can help everyone understand it at once. There was a second question asked about a train, so I want to briefly look at that. This is number 13 now. Train is traveling down a track and applies the brakes, it slows down. How far does it move during this interval? This is going to be a textbook case of using formula number 3. Because here we've got train with an initial velocity that begins decelerating over time, and you want to know how far it goes. Formula 3 is built for this purpose. Delta x is how far it goes while it's slowing down. You get initial speed, the time you're slowing, and your acceleration while slowing. You just want to make sure to plug in that -1 for A, because you are specifically slowing down. Oh! Nope, you know what? I assume you did that.
You get 0.
Okay, I apologize. That's because there's a trick to this that I forgot. I apologize. There is a hidden trick to this one. The problem here is, and this is true for everyone, everyone's numbers are slightly randomized, but whoever coded this question coded it in such a way that the same thing happens to all of the randomized versions. It only takes half of this time to actually stop. It says, how far does the train move during 66 seconds? But the train comes to a complete stop after 33 seconds. Or if you were given a time of 60 seconds, it comes to a stop after 30. Whoever wrote this coded it such that it always stops in half of the time it is asking about. And if it stops, that acceleration stops being true. Because if it comes to a stop, and stays stopped, it's no longer still accelerating backwards. So that acceleration is only true for half the time. I'm going to try to demonstrate using these numbers real quick. A equals delta V over delta T. -1 equals VF minus 33 over, I'm just going to put in 33 seconds. 33 times -1 is -33 equals VF minus 33. Add 33 to both sides, VF is 0. VF is 0. So, for every single one of you, the train stops in half the time allotted. And that means that it's really only slowing down for 33 seconds instead of 66. And so to get the actual correct answer, instead of using this time, you need to use half of it. Because this formula only works for the amount of time that acceleration is true. And that acceleration is only true until it stops completely. If you do put in the 66, like I mistakenly said to do at first, this would be what would happen if the train came to a complete stop and then kept accelerating backwards, back to where it started. Whoever wrote this one is mean. I apologize. So I'm very glad you asked. How do you guys feel? Once again, please ask me homework questions in class. I want to make sure everyone gets this information. I will waylay an entire lecture if someone needs help with the homework. Yes?
For problems like this, would you only use halftime if the initial velocity is exactly half the time interval?
No, this one is only, this is a trick question, unfortunately. It's coded such that it gives you twice the time needed to slow down. And you'd only know that by doing it wrong the first time. Because when I looked at this the first time a few years ago, I ran into the same issue, and then I noticed that if I figured out the time it took to slow down, like to hit 0, it was half the interval given. Now, it is coded such that, because notice everyone has a deceleration of -1, meaning every single second your speed decreases by 1. And so within 33 seconds you'd hit 0, but if you keep that same acceleration for 66 seconds, then your speed would decrease all the way to -33, which again would be turning around instead of stopping. So whoever wrote this one is being mean, and I need to edit it for next year. Yes?
So then what's the initial velocity for?
This is still the initial velocity,
Okay.
because this is the velocity at the start of the process. The trick, the way they're trying to trick you is they just give you more time than is needed to hit a speed of 0.
Got it.
Because realistically, if you want to stop, you stop accelerating once you hit 0. If your goal is, I want to stop moving now. You don't, normally you hit the brake, you don't throw it into reverse. Feel good, I hope? All right. Now, main thing in terms of our normal lecture material that I wanted to do today is keep practicing 2D motion and vector addition. So this is just a bit more, nope, it's not visible yet. Why is it not visible yet? There it is. More trig practice, more vector addition. And this will be kind of the tail end of chapter 3. So we finish this one up, we'll be done for the week, and then next week we start learning about Newton's laws. So here we have two vectors that need added together. You can consider this to be two different parts of a height, here we've got walking 20 meters in this 40-degree direction, and then 40 meters in this 25-degree direction. And from start to finish, if you walk both of these vectors one after the other, you're gonna end up here. And so if we add these two vectors together, we will figure out the location and then magnitude and direction of our overall displacement. So, last time when we talked about adding vectors together, we discussed that you have to add their x components together and their y components together, which means we need to know what those components are. Right now we've got magnitude and direction form for both of these. We need component form for both of these. So whenever you're given a magnitude and direction vector, you can always turn it into a right triangle. Usually you just, the method I recommend is just taking the initial drawing and then from along this dotted line here representing the original axis, draw a line out for one axis, and then go to the tip of the vector and just draw a line straight down to intersect to it. So folding the legs out from the vector given, we would have an x piece and a y piece. And then same thing for the blue one, its own x piece and y piece. I don't have a blue marker, so I'm going to use black and green for that one. And in order to add these together, to figure out where this spot is, we need to break these down to their components first before we add them together. Because if we just add 20 to 40, it's not going to work because the 20 and the 40 are not pointing in the same direction. Questions so far? Okay. So, going one after the other, I'm just going to call the red vector 1 and blue vector 2. We need the x and y components of each. So here I've got labeled x1 and y1. In order to figure out what these are, you have to employ trace amounts of trig. So I've got SOHCAHTOA written here. And to use SOHCAHTOA, let's just review quickly which leg is opposite and which leg is adjacent in comparison to that 40 degrees. Very good. Y is going to be opposite because it's not touching the 40. That leaves x as adjacent by process of elimination. Now we've got the hypotenuse and one angle, so we're good to use sine and cosine to find the other two legs. Tangent's not going to be useful yet because it's opposite over adjacent. We don't have either of those yet, so I'm going to recommend sine and cosine for this one. Yeah. Sine dictates sine of our chosen angle will equal opposite over hypotenuse. So to fill in the details for this particular question, our theta is 40 degrees. We decided the opposite leg is going to be y, and our hypotenuse is the slanted 20. Tangent's not going to help us yet, because if I did write that out, it would look like this. That's two unknowns, not useful yet. So instead, I'm going to write out cosine of 40, which would be adjacent over hypotenuse, x1 over 20. So, using this information, I'd appreciate if you guys could calculate those two legs for me. This will also be a good check to make sure your calculator's in the correct mode.
You want
Yes.
x1 is 15.32, y1 is 12.86.
Very good. And when I'm writing out my components, I usually like to include some indication of the direction that that vector points in. It would just be the same direction as the arrow on the legs. The original vector here points both right and up. So the x leg points right, positive x, and the y leg points up, positive y. Questions about this part? Go good? All right, gotta do the same thing with the other one. It'll be virtually an identical process because even though the lengths and angles are different, the orientation of the triangle is just a mirror image. So the same logic should apply for x being adjacent and y being opposite. So if we just swap the numbers around, we'd have sine of 25 will equal y2 over 40, and cosine of 25 is x2 over 40. Does that track? Now, while you're finding those numbers for me, please, I will just point out that sine is not necessarily guaranteed to give you y, and cosine is not necessarily guaranteed to give you x. In this case, that does work on both sides, but again, it depends on the perspective of the triangle you're studying. Because if you instead write it like this, x is opposite, and it would switch. So do make note of the orientation of the triangle you are currently studying. And let me know when you guys have answers to these ones.
I got y2 is 16.9, x2 is 36.25.
Very good. And once again, I'm using arrows to indicate both direction and axis. Note that the blue vector points up and left, so the y leg points up and the x leg points left. It's another reason why good pictures are important. All right, any questions breaking these down to their components? All right. Now once you've got the components, actually adding them is very straightforward. You just want to make sure to add x with x and y with y. So I will just write these out oriented vertically. Our first vector has an x leg of 32, and a y leg of 12.86. Our second vector, an x leg of 36.25 and a y leg of 16.90. And we just add them together. Any issues?
So would you subtract the x values because they're going in opposite directions?
That is correct. I left a small mistake in on purpose. Notice that the x legs of each of these triangles point in opposite directions within the same axis. This is something unfortunate that happens because your calculator, as smart as it says on the packaging, is actually secretly really, really dumb. Because calculators can only do what they're programmed to do. And your calculator does not fully grasp the orientation of the trig that you put into it to get this number in particular. Your triangle can't see the image to know this is pointing in the negative direction. All it knows is the numbers you gave it. And those numbers were devoid of direction for the most part. So your calculator could not give you negative 36 even though you need negative 36. Since that x leg points leftward opposite this one. So one of them has to be negative since they work against one another. If you do not manually install that negative sign, you're gonna get a final answer here of something to the effect of, these add up to your x-axis will be correct, so that's not an issue. But your y-axis, if you don't manually add that negative sign, you're gonna get a final x answer of 51.57, which if you draw out this vector would look like this. Whereas instead, our x vector, our final vector overall, needs to tilt this way, mostly up, a little bit to the left, as opposed to a lot of it to the right. And again, this is sadly something your calculator cannot intrinsically tell you because your calculator's dumb and it can't see the image to interpret the context. This is why it's important to keep in mind these are logic puzzles based on reality, not just math class formula crunching. We look at the picture, we can tell that the two x's work against one another, and we typically decide that left is negative x. So one has to manually add that negative sign, and when you do that, you should get the anticipated negative 20.93. And that more accurately describes the actual final vector. I draw each piece out. We got vector 1, vector 2, and from start to finish, vector 3, with the 20.93x component and the 29.76y component. So the solid lines are the original two vectors and our final summation vector. The dotted lines are the components of the final summation vector. How's that feel? Does the inclusion of the negative make sense, is my goal. All right. And that conveniently does form the final answer in its component form. That is one way to fully describe this vector that takes you from the starting point to the finish point. Now, that said, there is another way to write a vector, and I would like to practice that one quickly. So we're going to take that component form and turn it back into a magnitude and direction form. So, what is the hypotenuse and theta of that triangle that we have created? And basically, this is just the reverse of how we started the problem. And there's more than one correct way to get the answers here. But off the top of your heads, how do you want to find that hypotenuse? Sorry?
Put diagram there.
Very good. I apologize if I don't always hear your good ideas. My hearing's not the best. Conveniently, if you keep the negative on your x answer, this formula squares it and gets rid of the negative, which is good because we don't want a negative going into a square root. So since it's squared, you can either drop the negative or keep it and it won't change anything. that hypotenuse should be approximately 36.4 meters. And that does complete the sides of our very wonky looking triangle. If we look at all three of the vectors in conjunction with each other. That is not a right triangle, unfortunately, but we don't have to worry about that. So that's our magnitude. How about direction?
Inverse tangent.
All right. Since we have all three sides of this triangle now, you can use any trig function, but I'm partial to tangent since we didn't use it earlier. Tan of our unknown angle is going to be opposite over adjacent, so that is 29.76 over negative 20.93. Again, your calculator doesn't always understand the negative and the directions, but I'm going to keep it on to show you what happens as a result, kind of explain what it means. So I'm going to keep the negative on. We'll just see how that goes. Our mystery angle will then be inverse tangent of 29.76 over negative 20.93. Inverse tan of your fraction. And please let me know if your math disagrees. I've got an angle of approximately 55 degrees. Any disagreements, complaints, etc.?
The angle would be negative because it's facing which is probably negative actual.
In this particular case, the angle is negative because it is clockwise. So I want to leave the negative in to kind of show what would happen in this particular case. Again, your calculator's kind of dumb. It's doing something a little bit insightful, but it might have gotten to that point accidentally. Mathematicians, that being the people who programmed your calculator, consider normal geometry, dang it, to involve a coordinate plane where left is positive x, up is positive y, therefore this is negative x and this is negative y, and that all angle measures start in terms of the positive x-axis and tilt counterclockwise from there. So, whereas a normal clock starts here and goes this way, mathematicians start here and go this way. Because they make their own rules, I guess. Now, because of that, your calculator assumes that all positive angle measures tilt counterclockwise, and therefore a negative one points clockwise, which technically does match the picture that I drew. That theta, the way that I drew it, is clockwise away from the axis I started it from. So this negative actually does make sense, and that's just what it would mean if you happened to get one in this scenario. It doesn't mean you got like an anti-angle, it just means clockwise. So does that feel okay for right now? All right, so that is magnitude and direction, so that is fully describing this summation vector here. So we are done with the question. I do want to use this answer as a jumping off point to bring up something related to the whole negative clockwise thing. And it's that angles always have to be in relationship to something else. All angles have a frame of reference. Because if I tell you 30 degrees, you don't know from what unless I'm specific or unless I am playing to very specific mathematical standards. Like if I told you to walk outside and then walk for 3 miles at 25 degrees, you wouldn't know what that meant necessarily. You couldn't look at a map and immediately know where I want you to go, because 25 degrees from what? And so on answers like this, and especially when reading some questions that will come up down the line, it's important to understand some of the conventions for determining the frame of reference on angles. There's a couple different ways that people write out those things, and I want to make sure that you've seen them and that those frames of reference make sense. If you read an angle by itself, like if I hand you a question written by me or written on the homework, and all it gives you is an angle with no picture and no context, a mathematician typically assumes it's counterclockwise from positive x. So just an angle by itself, it is assumed this is your frame of reference. That means that if we left this answer alone, as is, it's not technically as correct as it could be. Because if we just write -55, a mathematician might look at that and assume, okay, no other axis was specified, so I'm going to start at positive x and then tilt clockwise from there, which points in the exact opposite direction as to where we actually wanted to go. Which means that since this doesn't necessarily play to normal mathematics standards, we have to add a qualifying statement. We need to specify what axis this is in reference to. The negative already handles the clockwise part, but we need to say what it's clockwise from. If you don't write anything, it's assumed the positive x-axis, which just isn't true in this case. I wrote this as clockwise from -x, and so that's what you write. A number of clockwise degrees from -x. And a mathematician would look at that and immediately know everything they need to know. The way that's written, how does that feel? As a statement specifying direction. Yes?
So you have to write from 36.38 at -54.8 from -x. That's how it's written.
Yes, if I was to try to give magnitude and direction as one big, long, final answer, that would be 36.38 meters at -54.88 degrees from -x. And that would be the final statement containing magnitude and full reference frame for direction. So that is the one sentence that fully describes that summation vector. And on both homework and on a test, I may ask you what is very specifically this statement describing the summation vector. Now the frames of reference can get kind of weird sometimes, and the only way that it really makes sense is with practice, especially considering that some textbooks and some test questions that even I myself write don't necessarily use X and Y axis in their description. Some of them use north, south, east, and west, given that in this class we are trying to measure reality. And in reality, a lot of travel vectors point and are specified in north, east, south, and west, instead of positive y, positive x, negative y, negative x. So the last thing I want to do today is just very quickly, I'm going to put a few vectors on the board, just directions, and I just want to talk about the different ways that their frame of reference can be written to practice the way that they are commonly written, that you might see them on homework and tests. So, four vectors, sorry. And let's just look at, looking at these, how would you write them in words to make, including a frame of reference, to make it absolutely clear what direction they're pointing in? Starting with this one.
What's the number?
Sorry, that's 30. That is 30 degrees.
Positive 30 degrees, from positive x.
All right? Yes, that absolutely works, because again, if you don't specify anything else, positive numbers are assumed to be counterclockwise, and it's tilting that many degrees away from positive x. The dotted line is always the origin axis, and then it's a number of degrees away from the origin axis. So, 30 degrees from positive x summarizes what is happening here. I'm now going to take that answer, and I'm going to turn it into compass form, so that you're exposed to it. Instead of in terms of the x-axis, the origin axis on this version is east. And rather than just spinning counterclockwise, it is specifically rotating from east towards north. So some people would look at this and write 30 degrees north of east. That meaning, again, it starts east and then tilts towards north. I understand it can be kind of weird that the origin is written second and the modifier is written first, but it's just a quirk of the English language. Yes?
So if you're using a compass and base it off that, you wouldn't have to use any negatives because it would just say south and east or southwest.
Correct. The north versus south inherently already adds positive or negative. It indicates the direction of spin. How does that feel, just for this one as an example? Okay. Take the same logic and look at this one. How would you write 60 degrees tilting this way from up?
Would it be 60 degrees from positive y?
All right. 60 degrees from positive y, that absolutely works. We don't have to specify any other direction because it's already counterclockwise. Positive already takes care of that. How would you do that in compass form? I hear someone saying it, but my ears aren't right, sorry.
60 degrees south of west.
Almost. We're actually starting north and moving towards west.
So north and west?
Yeah, if it helps, you would find the starting axis and then use the next letter it's moving towards. So you are correct, it's becoming more south than it was, but you pass through west first on your way there. So this would be west of north. This one's real tricky. What do you think of this? South. South, just south, or negative y. Optionally, you could call this 270 degrees if you wanted to. And then lastly,
45 degrees east of south.
you'd actually reverse that because it starts east and tilts
Oh, yeah.
towards south. So, south of east. Or alternatively, you could just list negative 45. Because if you don't specify any other axis, you assume positive x. Unless there's a picture that gives you other context. How y'all feel?
Wouldn't it have to be negative 45? Just going clockwise?
Yes, sorry.
Oh.
Well, see, the picture takes care of the negative, but if we're writing it out in words, yeah, negative 45.
Okay, so you you don't have to put the negative if you're saying south.
Correct. The south handles what direction it's moving. It's a weird system, I admit, and it's also not perfect. So we're gonna keep practicing it. I wanna make sure you've been exposed to it. And then if you guys need anything over the weekend, have a great weekend. That's it.
Have a good day.
You too.
I'm sorry.